Hello everyone, welcome back to this video for the course of Introduction to Data Science. In this video I will explain you how we can handle missing values. We discussed briefly three different methods to handle missing values. Let's now illustrate these methods in a simple example. So what we are going to do is the following. First of all, we want to understand what is the effect of a certain method for handling missing values on my results. Of course, there is one problem that if you take a data set with missing values, then you don't know what is the effect of your method, because you apply your method to get rid of the missing values. You can determine your results, a mean or a variance, or apply a statistical model on your pre-processed data. But of course, you don't know what the results would be if there are no missing values, because you only have a data set with missing values. You don't have the original data set. Therefore, we will do something else. We are not going to illustrate how the methods work on real data sets. Instead, we will work with synthetic data sets that we created. And the advantage is the following. If we simulate our own data, then we know exactly what is going on. It means that we can control all the factors affecting the data. So in our case, I want to have a nice and clean data set with only missing values. There shouldn't be any other problems with the data. For example, later on we talk about outliers. Well, now I only want to study missing values, so I do not want to study a data set with missing values and outliers. Right? A second advantage of using simulated data, synthetic data, is that we can quantify the effect of our method, because we can compare. We can compare what the result is without any missing values, and we can, because we know what the data is, we know where the data is coming from, we added the missing values, so we know what we did with the data, how we distorted the data, so we can compare with and without missing values to see what is the effect. We can quantify that effect. All right, so what we are going to do is the following. First of all, we create our original clean data set. And we do that with this line of code. We use the rnorm function in R. Rnorm means generate randomly 1000 normal distributed random variables, where I tell R what is the mean and what is the standard deviation of my normal distribution. So if I run this code, I have a vector, which is in this case called data, which are 1000 simulated normal distributed random variables. And for example, I can calculate the mean of my data set, which is 100.42. I know that it should be 100. It is not equal to 100 because, well, data is random and there is noise, so you have distortions. If I would take 10,000, 100,000, 1 million simulated values, that empirical mean is coming closer and closer to 100, of course, right? What you can do at home, for example, is you can plot a histogram of the vector data to see if it's really a normal distribution. You can even compare it with the theoretical density of a normal distribution with mean 100 and standard deviation 25 to see if your data is indeed coming from a normal distribution. Okay, we continue, and what we do is we will say, well, we start with the data set data, but we want to transform it in a data set, which I call data.missing, which now contains 200 missing values. So I use for this the function sample, which randomly takes 200 numbers from 1 until 1000. And these are the locations of my missing values. So I have my original data set, 1000 normally distributed realizations, no missing values, and now I pick randomly 200 out of this data set, and I say, well, these numbers that I see there, I replace them with a missing value. All right, what we did is we had our initial data set data. It was the nice clean data set, no missing values. Then we transformed the data set in the data set data dot missing. This is the data set that you see. So if you start your, say your data science project, then what you get is this data set. So this is our data scientist. He sees that data set with the 200 missing values. Of course, if you want to calculate the mean, for example, of your data, you cannot use the data.missing dataset, or you cannot directly use it because it will give you an error. Instead, what we are going to do is we are going to create a new dataset, which in this case I call the dataset data.remove, which is a new dataset based on the data.missing dataset, but now I remove all the missing values. I had initially 1000 observations. This is a dataset with 1000 observations. After I remove all the missing values, I end up with a dataset with 800 observations. So what I do is I take my original data with missing values. I check, do we have missing values and where are my missing values? I then say, let's take data.missing, and this minus sign here tells you you have to subtract, you have to remove all the elements that are here. So the which function indicates where are my missing values. With the minus, you take the data.missing vector and you remove all the missing values. All right, so then my data.remove is a dataset without any missing values, and for example, I can calculate a mean. In this case, the mean is 100.25. We call that the theoretical mean is 100, that's what's based on the simulation. Then the empirical mean of the dataset without missing values was 100.42. So you see that by removing some of the observations, I changed my mean, but in this case, we are still close to the mean of my original data sets. All right, so we simulated a data set. We said we have 200 missing values, so we will randomly select where these 200 missing values are located in my data set. And then I create a new data set where I remove all these 200 missing values. I calculate the mean. Let's now repeat this. So I simulate a data set, I add missing values, then I remove these missing values, I calculate the mean. But now I change the number of missing values. So here on the x-axis, I have how many missing values I have. So in our example, we had 200 missing values. But if I repeat this, I can say, let's now do 100 missing values, or 300, 400, 500, and so on. And then I plot the mean that I calculate each time on the y-axis. And what you see is that the variability in the mean, the fluctuations in the mean, are becoming larger and larger. We have here, say, in the middle, we have the 100.42. That was the mean of my data set where I did not have any missing values. And you see, as long as I have only a few missing values, say as long as I am here, less than 100 missing values, from time to time the mean that I get when I remove the missing values can be a little bit larger, a little bit smaller, but is in the neighborhood of the 100.42. Otherwise stated, when I have only a few missing values, I do not change my mean too much. The impact of removing data is not dramatic. However, the more missing values my data set contains, the more fluctuations I can expect. If I have, for example, 500 observations, well, you see that your mean can be much larger or much smaller than where you want your mean to be. So it means that removing missing values is a good approach, but you have to take into account that you have a variability in your estimates. And especially if you have many missing values, this can make your predictions unstable, because you have too much noise, and it means that it's not that reliable anymore what you calculate. Alright, so the problem with method 1 is that your estimates, when you remove the missing values, become unstable if you have too many missing values. Which is something that I hope you know, that if you calculate, for example, a mean, then your prediction of the mean becomes better, more accurate if you have more data. If you take a mean over a very small sample, it's not that meaningful anymore. So now we move to method 2, where we say, well, we do not want to remove data, because removing data means we have a smaller data set, and that has an impact on the variability of our estimates. So instead, I'm going to replace my missing values with something else. So okay, we have our data set data.missing. So that's the data set where I have 200 missing values. I'm going to use the replace function in R, which says the replace function starts with the vector data.missing. Then it says, well, what are the observations in that data set that you want to replace? Well, I use the which and the is.na to locate the missing values, but these are the values that I want to replace. And if I have located the missing values, I have to tell R with what value do you want to replace these observations. Well, I take the mean of my data set without the missing values. So I say, well, this is the mean of the observations that have no missing values, and if there is a missing value with one of the other observations, I just plug in the mean. Okay, so my vector data.replace is now a vector with 1000 observations. So the vector data.remove of the previous slides was a vector with 800 observations, because I removed all the missing values. Data.replace, again, 1000 observations. However, let's look at the standard deviation of my original data set. So data, where my 1000 observation of a normal distribution, where I do not have any missing values. Then the standard deviation is 25.76, and in the theoretical standard deviation was around 25. If I now look at my data.replace vector, so again 1000 observations, but 200 of them now are replaced, have missing values, so I replace them by the sample mean. Now suddenly my standard deviation of my pre-processed data set drops to 14.48. It is much smaller than my original data set. We can investigate the effect of replacing missing values with the sample mean using the same approach we did with method 1. On the x-axis, I indicate how many missing values I have in my data set. So I just repeat what I did on the previous slide. I have my data, I generate 1000 observations. I say I have, for example, 100 missing values. So I randomly select 100 observations. I add missing values. And then I say I start with that data set. I locate the missing values, 100 in this case, replace them with the sample mean and calculate the standard deviation. And then I say, let's do 101 missing values, then 102, and so on. And each time I get a standard deviation. And what you see is that the standard deviation becomes smaller and smaller if we have more and more missing values. And of course, this, I hope, is intuitively clear. Because what is a standard deviation? And standard deviation tells you something about the variability of your data. How much is your data moving around its sample mean? But what I do in this second method, I'm replacing my random numbers that now are replaced by missing values. I replace them again by the mean. So it means that I replace it by something that is very close, that is exactly equal to the mean. And then I want to know, well, what fluctuations can I expect? Of course, these observations that are replaced by the sample mean have a very small standard deviation. So I am reducing the variability in my data set because I always replace missing values by something that is close to the mean. So the major drawback of method 2 is that the variance of the clean data set is smaller than my original variance. And what does it mean that I have a smaller variance? It means that that variable is becoming more predictable. Like I said before, the variance tells you something on what fluctuations can I expect. And of course, more fluctuations, higher standard deviation, means that your variable is less predictable. And of course, in data science, we try to predict something. We try to predict the weather or the stock markets. Now I make my dataset more predictable by replacing observations by the sample mean, but that maybe has an effect on my later data science results. Maybe for my project, it turns out that we can very accurately predict this variable, whereas that accuracy is mainly driven by the fact that you replaced many of the observations by the sample mean. So for method 2, we have to be careful. Although we keep the number of observations the same, still 1000, I make my variable more predictable, and that can have its effect. To illustrate method 3, I'm going to create a new data set. First, we have a variable x, where x is the same as before, normally distributed, some mean, 1000 observations, a mean, and a standard deviation. Variable y, my second random variable, is a function of x. So if you know x, then you have to simulate here a normal distribution. You simulate a normal distribution and you connect them together to get y. So if you run these two lines of code, you have x and y. And for example, you can try to make a plot to illustrate the dependence between x and y. Yeah? And I put this information, this data set, in the matrix data. So what I'm going to do then is I'm going to add the missing values. Again, 200 missing values, and in this situation, there are only missing values for the first variable x. So we have x, we have y, x has missing values, but y has no missing values, just to keep things simple. And again, I randomly select 200 observations in my data set, and I say, well, this is a missing value. So it's the same as in the previous two methods, but now we have x and y is a function of x. So we have our dataset data.missing, and in method 1, method 2, data.missing was a vector. You have only values for x there. In this situation, method 3, data.missing is a matrix. You have x in the first column, y in the second column. So I'm going to replace the missing values by new values. So I work in the spirit of method 2, in the sense I do not want to throw away data. I want to create a new data set, data.replace.x, which is the new data set, which again contains 1000 observations. Okay, so that's the same as in method 2. However, I'm going to replace the missing values not with the sample mean, but with a randomly generated number. So if I use the replace function again, I say, well, there are only missing values in x, so in the first column. So I'm going to only look at the first column, data.missing. This indicates the comma 1 indicates I take the first column. I locate the missing values. So I'm going to use the replace function, and the replace function should replace the values that contain the entries that contain missing values by a randomly sampled value from the vector values.x. And what is value.x? It's here. Values.x contains all the values that appear in the first column. So I take data.missing and I delete all the missing values. And I take only the first column because that's where the missing values are located, right? So then I'm going to randomly pick a number from one of the observations that I had, right? And I put that instead of the missing value. Right? So I'm going to replace the missing values, but not by the sample mean, but by something that I observed already. For example, assume that I have grades, and for one student, I have no grades. I just randomly select a grade from all the other students. I say, you have the same grade as this student, and I put it in. Yeah? What you see is, if we calculate the standard deviation of my new data set, where I replace the missing values, is 25 something, which is very close to the standard deviation of my dataset without any missing values. Right? So with method 3, I do not have that problem where my standard deviation is becoming very small if I replace many missing values by the sample mean. In this case, 200 observations, I replace the missing values by a randomly generated number, and what I find is that it has very little effect on the standard deviation. However, let's have a look at our original dataset. In our original dataset, you had x here, you have y here, and you see that there is a very strong linear relationship between the two variables. What I did is I replaced each of the missing values in x by something randomly generated from the observed values in x. And in that procedure, and you can check the R code, when I replaced the missing values of x, I never used any information on y. So you can replace the vector y by something completely different that has no effect on how I handle missing values for x. Which you can think of something good. The problem is that there is a relation between x and y, and I'm not using that relation when I replace the missing values. And that's what you see here. My data set that I'm going to use after I replace the missing values by randomly generated numbers has problems here and here. You destroy that very strong linear relationship because when you handle the missing values, you do not use that very strong linear relationship. So R doesn't know it should use it. So that's one of the problems with method 3. It works very well in one dimension, but if you work in multiple dimensions, it does not take into account the dependencies between the random variables. So to summarize, we find that method 1 and method 2 work well as long as we do not have too many missing values. And we know that method 1 will have an effect on the variability of your estimates. Method 2 has an effect on the variability of your data set, the predictability of your data set. Method 3, on the other hand, does not affect the variability of your observations, but it may have a problem if you have multiple variables that are dependent of each other. Then, apart from showing how these different methods work and what is their impact, I think it's also important that you understand how we can use synthetic and simulated data to understand certain data science methods better. So it is not always the best approach to directly start with real data, because real data is noisy. You don't know exactly where the data comes from, and working with, as a first step, working with simulated data helps you to understand what the method is doing and gives you a way to quantify certain effects, because you can compare what the result is with your methods and what it should be, because you know what the data is, exactly where the data is coming from.